Hi, and welcome to the 6th video in my homemade CPU series. In this video we're going to be looking back at the address register. Now, just as a quick reminder, we've got the input and output from the bus here. We've got a bus driver chip here, which is the 574, and we've got the 193 up-down counter. Now, our address registers will be 16 bits wide. This is only 8 bits wide, but when we actually make up the final form, we can double up all of this componentry, and it's far easier to develop and test at half size since it all fits onto one breadboard. Now, in each of the past videos where I've dealt with the address registers, I've tried to focus on one function or one piece of logic. So this video is a little bit different in that I'm kind of going to quickly go through a number of smaller things about this register and small additions in order to finish it up. So it's basically the things that wouldn't really fit in anywhere else. So firstly, I'd like to talk about these extra 8 wires I put in here. At the moment, it's just got an extra set of output LEDs on it, which is showing the current count state. But I did put these wires in for a different purpose, and that was these registers, rather than being connected to one 16-bit bus, they're actually going to be connected to 2. Let me explain how that works. So if we go back to the block diagram we started this series with, I've talked about the 16-bit registers down here, and they would be connected to the address bus, and obviously they'd be used to address the 64 kilobytes of memory. Now, long before I started making these videos, and I was originally just thinking all of this out, my first thought was that I would have a singular 16-bit address bus that would pass through all of these registers and connect them to memory. Now, the more I thought about this and the more I looked at some actual applications of this processor, how I would be performing particular options with the instruction streams, the more I realized that this was potentially going to be a performance bottleneck that I could deal with. Now, one of the attributes of this processor, one of its most important attributes, is the fact that it's going to be pipelined. And what this means from a performance perspective is that every single cycle we would like to be able to load an instruction from memory and dispatch it into the pipeline, and then it would complete a certain amount of time later with multiple instructions being in flight at any given point in time. Now, we're not actually going to manage that, but I'm hoping we're going to get quite close to it. And the reason we're not going to manage it is because there's going to be some resource clashes. And the most important resource from this point of discussion is accessing memory. And so what we're actually going to see is every single clock in which nothing else is accessing memory, the fetch unit will fetch an instruction and dispatch it. So any read or writes we do to memory further down in the pipeline, we're going to need a mechanic in place that can grab hold of the address bus and suppress the fetch unit. Otherwise we'll have a clash and it's not going to work right. But in my original plan here, I was thinking, well, I've got to be able to get 16-bit quantities in between these registers. Now, my thinking there was that I would give them all of these registers are going to have to be able to assert their contents onto the address bus. But if I also gave them the ability to read it off the address bus, if I needed to move a value between two registers, then this wouldn't be a problem. I would reserve the address bus but not be accessing memory. I'd tell a register to assert onto the bus, and then whatever register was loading it would pull the value back out. And that would work. But obviously this would mean that nothing in the pipeline could access memory during that cycle, and the fetch unit, most importantly, wouldn't be able to fetch a new instruction. So what I have since decided is that I would put a second bus in here, which was going to be dedicated for moving data between these registers. Now, if you're used to people talking about the bus, this might seem a little bit strange, but by the time we're done on this, we're going to have quite a few more buses. And actually, this additional bus is going to not take very much. Now, for starters, this bus was going to have the load and store functionality, but the load and store functionality needs to go over here, and the main address bus can actually be a lot simpler. The registers only need to be able to write to it, and that makes our life a little bit easier. So all we actually need is an extra set of lines coming out from the chips, just directly cascaded off the lines that are going into this line driver chip into a Nava line driver chip, or on the final 16-bit version, a pair of them. And that will get us what we want. Sorry, brand new chip. I need to roll the edges of this a little bit. Now, this chip is also a 574, but there's something else that's difficult about it, which different about it, that I'll bring up in a moment. So if I connect the power up to this, I will also need to duplicate this line over here. Remember, this is the load line, which we're triggering every clock cycle, so that the bus drivers have a stable copy of the data contents of the register. So in theory, if I were to move this over here, and bring the output enable low, then it too can output the content. I'm very pleased to see that, and I will explain why I'm more pleased than it looks like I should be in a moment. But anyway, that is the second bus that we will be driving. Now, the reason why I'm slightly happy that this worked just as we expected it to is because it's not actually a 7.4 LS574. It is actually a 7.4 HCT 574. Now, the 74 series chips are fairly standard. There's a great big long list online you can go and take a look at that will let you see a lot of the different bits of functionality that you can get from those. And at the very beginning, when I started looking at this, I spent a great big long chunk of time going through the list thinking, okay, that's handy, that will be useful. And that's why I've been able to select some fairly interesting chips, I hope, to utilise in this build. But you have to be careful a little bit, because you look at one list of the chips and you see one that's particularly interesting, and then you go and look on eBay or Amazon or wherever, and you discover you can't actually buy them. Some of them are available occasionally, some of them only a small number of suppliers have, and some are only available in particular packages. And it turns out that the LS, which stands, I believe, for Low Power Shakti, my pronunciation on that last word is probably way off, is on the decline in terms of utilisation. Although I remember the electronics catalogues I used to look at as a kid being full of these things. They're not so common anymore, and particularly some of the more interesting smaller packages are it's very rare to be able to get them in that. Now, what you get is there's actually a whole variety of different variations of these chips that all have, if they've got the same final digits, they have essentially the same pin configuration. But if we talk about some of the very common ones, LS is your classic kind of TTL line standard. You also have HC, which stands for high-speed CMOS, and they are interesting. CMOS is the result of a whole set of research into the good way to make gates, and it's actually, CMOS is where pretty much all the current processors is the technology they use. So maybe we should look at that. But exploring the field a little bit more, it became very clear that the HC chips, they're a little bit more complicated, they're slightly more difficult to drive, and they have some extra considerations. But there is a third one that did interest me, and most importantly about the HC stuff is they're not compatible with the LS chips. We would have to look at a whole other set of chips for being able to do that in the HC series CMOS. But there is a third type that was particularly interesting, which is HCT. And HCT is effectively these CMOS HC devices, but they have TTL compatible inputs. So I don't know how they do that, and it's probably not universal between all the manufacturers, but the inputs and outputs of these conform to the TTL specification. So in theory, for the most part, I can mix and match them with these chips, and this additional line driver I put in was actually a HCT chip. These have these particular ones have very faint markings on them, so I'm partially pleased it worked, just because this arrived in a package, and it was only based on what I had ordered was I able to determine what it should be. But I was also aware that there are still some slight differences between the HCT and the LS in terms of line levels and such that could cause me some problems. So I'm relieved to see it work. Now, I also managed to secure a single 193 HCT chip, which I'm going to swap out this counter for. I'm actually going to be sensible and disconnect the power for this. Now I'm not too worried about using the LS series chips in my kind of working builds, but one of the reasons why I'm looking at these other HCT chips is they're a lot more commonly available in the surface mount packages, and I'd quite like to give the surface mount chips a try. Because it will make my circuit boards a little bit smaller. And every other idea I come up with seems to make them bigger, so something's got to give. Okay. Right. That is a terrible mistake. If you notice where the ground and power lines are, is that they don't actually line up with where they should be. I've put this chip in slightly the wrong place. So I'm actually going to be lucky if I haven't blown this chip up. The CMOS chips are renowned for being slightly more sensitive. Although I know that's particularly static electricity they're more sensitive to. Okay, we're getting some odd behaviour from that. I'm going to try something here. Okay, this is working right now, and all this was I've been relying on the way that the LS series chips, when you leave an input disconnected, they have a tendency to float high. I believe there's a internal pull-up resistors on the inputs, whereas these chips evidently don't have it, or don't have it strong enough. So I needed to actually pull this line high manually. The fact that I had first put it into the ground rail and it didn't work right was a nice little reminder that I have to leave the inputs on these particular counters high if I'm not when I'm not using them. But that too is working. I'll have to make a strong mental note of the fact that I can't leave the lines disconnected, even if I'm not going to use them. I need to pull them in the right direction. But that is successful. Okay, the third thing I'd like to look at is simply the next step is going to be to transfer these onto a PCB. So I'm going to design a PCB up, and one thing I would like is to not only have the LEDs for the data contents, but I'd like to add some LEDs for the various actions we're putting on them. So I'm just bringing in some resistors. Now, if you remember in the last video, we looked at the demultiplexer chip. And we're going to say, for example, for the assert to address bus, we'll have one of these chips and 8 outputs, with one connected to the output line for the demultiplexers. We'd have a similar set of outputs for the AVA bus, and it seems like it would be the right thing to do to, instead of having a row of 8 LEDs wherever this chip ends up, have the asserting to bus LED next to the register LEDs on the register. Oh, another thing that was mentioned to me by one of the very few people who've been watching my videos as I go. When I moved these wires from the bottom of the board to the top of the board, and these LEDs went from being on when they weren't selected to on only when they're selected, apparently what I said there wasn't very clear. So I will explain what I'm doing a little bit better here, hopefully. Now the LEDs, they come on when we put a voltage across them. And normally we think of the output lines from any of these chips as being the source of that current. So, but that doesn't necessarily have to be the case. Now what I'm doing when I run these LEDs the opposite way is, if you think of this LED, now assuming I've put it in correctly, the top lead of this LED is where we want the positive voltage, and the bottom lead of this LED is where we want the ground. So if I connect this LED to ground, it will come on. Now normally what we're doing is sticking the voltage coming out of a pin into the top end of this, and we're running a current through to ground. But if instead of doing that, I actually, say, take this let's fill it out a few more of these LEDs. If instead of connecting the LED to, so that its voltage input is connected to the pin and its output is connected to ground, what we do is do it the opposite way round, where we go from connect the LED directly to the 5-volt rail and then connect the other side to the pin. What that means is when the pin is high, both sides of the LED are going to be at 5 volts and no current will flow. We've got no voltage difference there. But then when the pin goes low, then we've got one input of the LED connected to the 5-volt rail still, and then we've got a source, a route to ground via across the LED. So and going into the output, because the output of a chip may be our logical output, but it can both source and sink a small amount of current. So this chip is currently being selected onto the bus. So if I put that wire in there, I expect it to come on, but if I change this line down here, which you remember goes via the inverter to select this chip, put that low, then the input here is now high and the LED is extinguished. So that's good. I'm going to need a slightly longer wire for this. I would like to also be able to have an indicator on the borrow and carry line. Now these are, the borrow and carries work on the positive edge, so when the line goes high. But if you remember the behavior of these, they actually spend, the borrow and carry lines spend most of their time high, and so if that's the carry line there, we're seeing this line will be set at 5 volts, and only if I clock it forward until this chip will carry. Then the LED will come on. Okay, so my current thinking is I'm probably just going to be using the borrow lines of these chips in the configuration I've got, which gives me an interesting way of detecting when any counting on them hits 0. But I'm going to bring both of these lines out of the register board, and I'm going to put indicators for both of them because it's a nice thing to have. So I won't bother doing the borrow because that's going to end up exactly the same. But the one other line that I think it's worth us having will be the load. So if I instruct this chip to load, that LED comes on. So we have a nice little row of 16 LEDs for the register contents, and then these 4 additional LEDs which will tell us what's going on with the register. Okay, so that's pretty much it. Apart from one thing that is worth noting is this load line on the latch chips that we're using to drive our buses. I've just cascaded this straight on, and the same will be true for the other 2 of these, which are driving the upper 8 bits of the buses. So this line is actually going to be repeated out to 4 chips, and I have realised that that's something that we actually want to pay a little bit of attention to. There is a property on the various data sheets for these various chips called Fanout. And the HCT chips, or the CMOS chips in generally, tend to have a slightly lower fanout, but lots of things will affect the fanout. And what the fanout means is if I've got a line with a logic signal on it, how many input lines can that actually drive? So if I took this logical line out and tried to set it as an input to 1,000 chips, then whatever chip I've got is not actually going to produce enough current to maintain the voltage level to send that signal to that many chips. And on some of the chips I've seen a value of 40 specified for the fanout, and on some it gets a lot lower. I think these ones actually have a fanout of 10. So for some of the lines, such as the clock lines that we're going to use here, that's something that we actually have to pay a lot of attention to, because if the whatever generates the clock has a fanout of 10, we're going to break that with the 3rd register that we try and stack onto it. Now we can resolve that very simply electronically. Is if you ever see on a circuit the symbol for a non-inverting buffer, this is exactly what we want to solve the problem. And we could potentially have a line fanning out to whatever the limit is of these, and then from each of the outputs from the buffer we could go to whatever the buffer chip is specifying as the fan out count. I did consider sticking a buffer chip onto the register board, but I'd only really have 2 possible uses for it. One for the reset line, which is fanning out to the 4 different chips clear lines, and one to the bus driving latch chips, and that's a little bit of a wastage because we'd only used 2 out of the minimum I found, which was a chip with 4 of these pass-through gates, and instead I think we don't need to make any changes to the register. We just need to remember that we're not just wiring these common lines to everything and expecting that to work. We need to divide them up a little bit, and that will enable it to operate correctly. Anyway, that's the 4 things I wanted to cover. I'm going to spend a little bit of time practicing on the PCB design software, and I may or may not make a video of that before I order a PCB for these registers, but I'll let you know one way or another. Thank you very much for watching.